In this video on integration, more specifically the method of U-substitution for definite integrals, we're going to evaluate the definite integral we see here. That is, the integral from 0 to ln of 3 of pi times e of x over, in parentheses, 1 plus e of x squared. Okay, well, to get us started, let me move this to the side a bit, like so. First of all, when looking at this integral, it's important to recognize that we're dealing with the method of substitution. And if you're a bit unsure of how to recognize that, here's the whole idea. Let me start by copying this definite integral, and I'll do that directly below. We need to find the integral from 0 to ln of 3 of pi times e of x over, in parentheses, 1 plus e of x squared. Okay. Now, to recognize that we're dealing with the method of U-substitution, it's important to see that this integrand, that's the expression we're trying to integrate, is a product of two functions, one of which is a composite function. And to make what I've just said more obvious, let me rewrite this integral as the integral from 0 to ln of 3 of 1 over 1 plus e of x squared times pi e of x. Looking at the integrand we now have, we can see far more clearly that we're dealing with a product of two functions. One of them being pi times e of x, the other one being 1 over 1 plus e of x squared. Furthermore, this function, 1 over 1 plus e of x squared, is definitely a composite function whose inner function, that's the function inside the other, is 1 plus e of x. And as soon as we have to integrate a product of two functions which matches this setup, so a composite function times another function, then there's a strong chance that we need to use the method of U-substitution. And here's how to actually do that. First of all, we need to define a new variable. And the way to do that is to focus on the composite function inside the product, and more specifically, to focus on its inner function. So that would be the 1 plus e of x here. And that function is what we'll define as our new variable, u. And in fact, underneath this, I'll go ahead and say let u equal to 1 plus e of x. Okay, now that that's established, our goal is to rewrite our integral in terms of this new variable, u. In fact, instead of calling this method the method of substitution, I much prefer calling it the change of variable method, because that's exactly what we're doing. So if u is equal to 1 plus e of x, then 1 over 1 plus e of x squared will just turn into 1 over u squared. But what about the second function in the product, this pi times e of x? Well, put simply, if we're indeed right and the method that's required to find this integral is the method of U-substitution, then we'll be able to rewrite the second function, so pi times e of x, as well as the differential dx in terms of the new variable u by looking at the derivative of u. In other words, by looking at du dx. So let's see, if u is equal to 1 plus e of x, then its derivative, du dx, will be equal to the derivative of 1, which is just 0, plus the derivative of e of x, which is e of x. And looking at this derivative, du dx, as well as the product we have here, pi times e of x times dx, we quickly realize that we can rewrite e of x times dx in terms of u by rearranging this derivative. Indeed, if I multiply both sides of this by dx, we obtain du is equal to e of x dx. And so using this result, we'll be able to replace this e of x times dx by du. And now that we've established these two results, we can go ahead and rewrite what's inside the integral here in terms of the new variable u. And I'll move over to the right to do that. And so at the top of the page, I'll say that the integral from 0 to ln of 3 of pi times e of x over 1 plus e of x squared is therefore equal to the integral, whose lower and upper limits I'll specify in just a minute, 1 over 1 plus e of x squared, which will turn into 1 over u squared. So I'll just write that. That's 1 over u squared times pi times e of x dx. So that will turn into pi times du. And so I write that here, that's pi times du right there. And I'll point out that this pi here can be taken outside of the integral and placed as a factor at the front here. And so just to simplify the notation, I'll just go ahead and rewrite this as pi times the integral of 1 over u squared du. Okay, so we've now rewritten this in terms of the new variable u. But what about the lower and upper limits of our definite integral? Well, put simply, the lower and upper limits of our definite integral need to be rewritten in terms of u as well. And here's how that's done. I'll write that in the far upper right-hand corner here, and I'll say the lower / upper limits. Well, let's see. We defined our new variable u as 1 plus e of x. And so I'll just rewrite that here. We know that u is equal to 1 plus e of x. And to find what the lower and upper limits are in terms of u, all we have to do is figure out what u will be equal to when x equals to 0, that's the lower limit, as well as when x equals to ln of 3, that's the upper limit. And the values we obtain will turn into the lower and upper limits of our integral written in terms of u. So let's go ahead. When x equals to 0, 2 dots, u will be equal to 1 plus e of 0. And since e of 0 is just equal to 1, this turns into 1 plus 1, which equals to 2. And so that's our lower limit, and I can already write that on my definite integral here and here. Next, I look at the value of u at the upper limit, ln of 3. So when x equals to ln of 3, u will be equal to 1 plus e of ln of 3. But remember, e and ln are inverse functions of each other, and consequently, they cancel each other out. So e of ln of 3 will just equal to 3. And so I can state that we have 1 plus 3, which equals to 4. And that's the upper limit of our definite integral. And so I can write that now. I'll add 4 up here and a 4 here. And let me separate this from the rest. There we go. And I should say, if ever rewriting the lower and upper limits in terms of the new variable makes you uncomfortable, don't worry, as I'll show you how we can avoid having to do that altogether at the end of this video. Okay, at this stage we need to evaluate this integral written in terms of u. And for that, all we have to do is find the integral of 1 over u squared. And since it's a definite integral, we can avoid any constant of integration. Now, when integrating 1 over u squared with respect to u, we find negative 1 over u. In other words, this equals to pi times, in square brackets, negative 1 over u, with lower limit 2 and upper limit 4. And if ever you're wondering how I integrate 1 over u squared and obtain negative 1 over u so quickly, here's a result I would recommend you know off by heart. When differentiating an expression of the form a over x, where x isn't equal to 0, so when differentiating this, we will always obtain the opposite of a, or negative a, over x squared. And you can easily prove this result on your own using the power rule for differentiation. But I recommend knowing this result off by heart. And the reason for that is simply that we'll often be faced with this type of expression to differentiate. Furthermore, knowing this result off by heart allows us to quickly deduce the following result. The integral of a over x squared is equal to the opposite of a over x, plus some constant of integration c. And this result is exactly what I used to integrate 1 over u squared with respect to u. And so, put simply, I would strongly recommend you know these two results off by heart. That being said, I go back to my integral here. Now, before evaluating this, I like to take any factor of negative 1, like the one I have here, outside of this pair of square brackets. In other words, I like to rewrite this as the opposite of pi, or negative pi, times, in square brackets, 1 over u, evaluated at the upper limit 4, minus its value at the lower limit 2. And all I have to do now is calculate. This equals to the opposite of pi times, in square brackets, the value of 1 over u evaluated at 4, so that will be 1 over 4, minus 1 over u when u equals to 2, so that's 1 over 2. We now have 1/4 minus 1/2, which is negative 1/4, so that's negative pi times negative 1 over 4. Finally, negative pi times negative 1 over 4 is just equal to pi over 4. And we're done. The integral from 0 to ln of 3 of pi times e of x over 1 plus e of x squared is equal to pi over 4. And that's the final answer. Now, as I said a couple of minutes ago, I'll finish this video by showing you how we can avoid having to rewrite the lower and upper limits in terms of the new variable u. And I'll do that on the far right-hand side here. I'll just create a box in which I'll insert all the working. There we go. So what I'm about to show you now will fit inside this box here. To avoid working with the lower and upper limits written in terms of the new variable, the idea is to ignore the fact that we're dealing with a definite integral and to start by finding the antiderivative of pi times e of x over 1 plus e of x squared. And to do that, we define exactly the same new variable u, and rewriting this integral in terms of u would lead to this line of working here without the lower and upper limits on our integral. In other words, when rewriting this integral in terms of u, we would still get pi times the integral of 1 over u squared du. And of course, when integrating 1 over u squared with respect to u, we'd still get the opposite of 1 over u, or negative 1 over u. And so keeping in mind that that result would be multiplied by pi, we'd get negative pi over u plus some constant c. So up until this line of working, there won't be any difference with what we did earlier on. But the difference comes in now. If we now rewrite this result in terms of x, which we do by replacing the u we have here by 1 plus e of x, this integral turns into negative pi over 1 plus e of x plus c. And I'll go ahead and box that result. This is the antiderivative of pi times e of x over 1 plus e of x squared. And so using that result, we can evaluate the definite integral from 0 to ln of 3 of pi times e of x over 1 plus e of x squared by stating that that must equal to, in square brackets, the antiderivative we just found, ignoring the constant c, so that would be negative pi over 1 plus e of x, evaluated at the upper limit ln of 3, minus its value at the lower limit 0. And taking the factor negative pi outside of this pair of square brackets, this turns into negative pi times, in square brackets, 1 over 1 plus e of x, evaluated at ln of 3, minus its value at 0. And I'll move over to the left-hand side to carry on with my working here so I don't run out of space. That will equal to negative pi times, in square brackets, 1 over 1 plus e of x evaluated when x equals to ln of 3, that's the upper limit. So that's 1 over 1 plus e of ln of 3, minus 1 over 1 plus e of x evaluated when x equals to 0, that's the lower limit. So that's 1 over 1 plus e of 0. And now, since e and ln are inverses of each other, this e of ln of 3 turns into 3. And so this first fraction turns into 1 over 1 plus 3, which is 4. So this first fraction here is just equal to 1 over 4. And for the second fraction, we have 1 over 1 plus e of 0. Now, e of 0 is equal to 1, so this turns into 1 over 2. So this second fraction is equal to 1 over 2. And so we quickly see here that we have negative pi times, in square brackets, 1/4 minus 1/2, which is exactly what we had up here. Consequently, this will equal to negative pi times negative 1/4, just as we have up here. And so the final result will be the same, that's equal to pi over 4. And we're done. So in summary, when using the method of substitution for definite integrals, we have two options. Either we rewrite the lower and upper limits of the integral in terms of the new variable, like we did here, or we start by finding the function's antiderivative written in terms of x, and then we evaluate our definite integral the usual way. And whichever of the two methods you choose will be accepted in an exam, so choose whichever one best suits you. That being said, that's it for this video.